Our galaxy may hold hundreds of billions of planets, and the strangest ones can have years shorter than a day, skies made of steam, or no star at all. The word planet sounds simple, but modern astronomy has revealed a huge range of worlds far beyond the 8 familiar ones in our solar system. In this video we cover rocky planets, gas giants, ice giants, dwarf planets, super-Earths, mini-Neptunes, hot Jupiters, ocean planets, lava planets, rogue planets, circumbinary planets, tidally locked planets, eyeball planets, diamond planets, Puffy planets, Chthonian planets, Hycean planets, Blanets, Pulsar planets, superhabitable planets. If you want every major type broken down in one place, subscribe. We do this for everything. Rocky planets are worlds built mostly from metal and silicate rock, with solid surfaces you could, in principle, stand on. In our solar system, Mercury, Venus, Earth, and Mars are the classic examples. They form close to young stars, where it is too warm for light gases and ices to gather easily, so heavier materials clump into dense bodies instead. These planets often have mountains, valleys, volcanoes, and impact craters because their surfaces are shaped by internal heat and collisions. Some can hold atmospheres, but smaller ones often lose them over time because their gravity is weaker. Earth is a rocky planet with liquid water and life, while Venus shows how the same basic type can become a furnace hot enough to melt lead at the surface. From solid worlds close to stars, the next step up in size leads to the giants, made mostly of gas. Gas giants are enormous planets, made mostly of hydrogen and helium, with no true solid surface like Earth's. Jupiter and Saturn are the best-known examples. They likely began as icy and rocky cores that grew large enough to pull in huge amounts of gas from the disk around a young star. Deep inside, pressure rises so much that the gas changes into strange dense forms. And on Jupiter, hydrogen may become a liquid metal that helps power a giant magnetic field. Their thick atmospheres produce powerful storms, bands, and clouds, and many gas giants have large families of moons and rings. Jupiter is so massive that it contains more than twice the mass of all the other planets in our solar system combined. If rocky planets are compact and solid, gas giants are bloated and stormy, and that opens the door to a related but distinct group, rich in heavier frozen materials. Ice giants are large planets like Uranus and Neptune that are smaller than gas giants, but still far bigger than Earth. Despite the name, they are not giant balls of ordinary ice. Astronomers use the word ice here for substances like water, ammonia, and methane that were frozen in the cold outer disk where these planets formed. Ice giants still have hydrogen and helium atmospheres, but a bigger share of their mass comes from those heavier materials, making them denser than Saturn and different inside from Jupiter. Neptune's winds can race faster than the speed of sound on Earth, and Uranus is tipped over so extremely that it seems to roll around the sun on its side. These planets show that not every giant world is built the same way. Once astronomers looked beyond the 8 main planets, they also had to define a smaller class that shares space with many neighbors. Dwarf planets are round worlds that orbit the sun but have not cleared other objects out of their orbital neighborhood. That is the key difference between a dwarf planet and a full planet in the current solar system definition. Pluto, Eris, Haumea, Ceres, and Makemake are the best-known examples. They are large enough for gravity to pull them into a nearly spherical shape, yet they still share their region with many smaller bodies, especially in the asteroid belt and the Kuiper belt. Pluto has glaciers of nitrogen ice, haze layers in its atmosphere, and mountains made of water ice hard as rock in that deep cold. Ceres may even have salty brines beneath its surface. Dwarf planets remind us that the solar system is not neatly divided into only big planets and tiny rubble. Beyond them, astronomers found many exoplanets that are bigger than Earth, but smaller than Neptune. Super-Earths are planets with more mass than Earth, but less than the ice giants, usually up to around 10 Earth masses. The name only refers to size or mass, not to surface conditions. So a super-Earth could be rocky, watery, or wrapped in a thick atmosphere. Many were found by planet-hunting missions because their larger size makes them easier to detect than Earth twins. Some may have stronger gravity, deeper oceans, or thicker air than Earth, while others could be hot, dry, and hostile. Kepler-10b was one of the first confirmed rocky super-Earths, and many star systems seem to have them, even though our own does not. That absence in our solar system is one reason these planets are so important. They may be among the most common worlds in the galaxy. Right next to them in size is another frequent class, that looks more like a scaled-down Neptune. Mini-Neptunes are planets smaller than Neptune but larger than Earth, with thick envelopes of gas surrounding a denser interior. They often fall in the same broad size range as super-Earths, which is why astronomers use density and atmosphere clues to tell them apart. A mini-Neptune might have a rocky or icy core hidden under a deep layer of hydrogen, helium, steam, or other gases, making it feel less like a big Earth and more like a little giant planet. These worlds appear to be very common around other stars. Some may have formed beyond the frost line, where ices were abundant, and then moved inward. Others may have started as rocky worlds, and held onto more gas than Earth did. The famous planet K2 to 18b has often been discussed as a possible mini-Neptune or related water-rich world. Some giant planets go even further inward, becoming scorched worlds called hot Jupiters. Hot Jupiters are gas giants about the size of Jupiter that orbit extremely close to their stars, often completing a year in just a few days. They are far too hot to have formed where we find them now, so the leading idea is that they formed farther out and later migrated inward through interactions with the gas disk or with other planets. Their close orbits heat their atmospheres to extreme temperatures, driving fierce winds and puffing some of them up to unusually large sizes. Many are tidally locked, with one side always facing the star. The first planet found around a sun-like star, 51 Pegasi b, was a hot Jupiter, and its discovery in 1995 changed planetary science overnight, because nothing like it exists in our solar system. Once astronomers realized planets could migrate, many other strange worlds made more sense, including planets that may be covered almost entirely by water. Ocean planets are worlds thought to contain huge amounts of water, possibly with global oceans hundreds of kilometers deep. They may form in colder regions rich in ice, and then move inward to warmer zones, where the outer layers melt into deep seas. Unlike Earth, which has continents and relatively shallow oceans, an ocean planet might have no exposed land at all. At great depth, pressure could turn water into exotic high-pressure ice, even if the upper layers are liquid, creating a strange stack of ocean above ice above rock. These planets are still mostly theoretical, but several exoplanets have been proposed as candidates. Their climates and chemistry could be very different from Earth's, because the interaction between rock, water, and atmosphere may be limited by those deep layers. If too much water creates a global sea, too much heat can do the opposite and turn a world into a glowing planet of molten stone. Lava planets are rocky worlds orbiting so close to their stars that their surfaces are partly or entirely molten. Daytime temperatures can climb high enough to melt rock, creating lava oceans, glowing ground, and even thin atmospheres made from vaporized stone. These planets are usually small and dense, and many are tidally locked, so one hemisphere bakes under constant starlight, while the other may be cooler. On some lava planets, minerals can evaporate on the hot side, drift through the atmosphere, and condense on the night side like rock rain. Kepler 10b and 55 Cancri are famous examples, often discussed as possible lava worlds. 55 Cancri may have temperature differences so extreme that its surface conditions could change dramatically over time. These planets show how familiar materials behave in utterly unfamiliar settings. Some worlds are stranger still, because they do not orbit any star at all. Rogue planets are planetary mass objects drifting through space without orbiting a star. Some may have formed in a disk around a star and then been flung out by gravitational chaos, while others may have formed alone in collapsing gas clouds, almost like tiny failed stars. Without a nearby sun, they are dark and hard to detect, so astronomers often find them through gravitational microlensing, when their gravity briefly magnifies the light of a background star. A rogue planet with a thick atmosphere or internal heat might still keep underground oceans warm for long periods, even in interstellar darkness. That means a planet does not always need sunshine to remain geologically active. There may be billions of rogue planets in the Milky Way, possibly rivaling the number of stars. After worlds with no sun at all, it is natural to look at planets that orbit not one star, but two. Circumbinary planets orbit around two stars instead of one, circling both members of a binary system. If you stood on one, the sky could hold twin sunrises and shifting patterns of daylight as the stars moved around each other. These planets must orbit far enough out to remain stable, because being too close to the pair would lead to a chaotic path. Their formation is tricky because the gravity of two stars can stir up the disk of material and make gentle growth harder, yet nature clearly manages it. Kepler-16b became famous as a real-life example, often compared with the fictional world Tatooines. Its discovery proved that planets can thrive in environments once thought too messy for orderly formation. Circumbinary planets show that stable orbits come in more than one design. Another orbital effect can shape a planet just as strongly, even around a single star, by locking one face permanently toward it. Tidally locked planets rotate in step with their orbit, so that the same side always faces their star, much like the Moon always shows one face to Earth. This happens because gravity slowly breaks the planet's spin over time until it settles into a stable rhythm. Many planets close to small, cool stars are expected to be tidally locked because they orbit so near their suns. That creates a permanent day side and a permanent night side, which sounds hostile, but a thick enough atmosphere or ocean could move heat around and prevent the air from freezing on one side or boiling away on the other. Some of the most promising potentially habitable exoplanets around red dwarf stars may be tidally locked, so this condition is not a rare curiosity. It may be common on worlds we study for life. In the most extreme versions, that split between hot and cold can create a very distinctive appearance. Eyeball planets are a special kind of tidally locked world, where one side faces the star and stays warm enough for liquid water only in a central region. Picture a frozen globe with a dark ocean or a warm patch at the point directly under the star, making the planet look like a giant eye from space. This idea usually applies to worlds orbiting red dwarf stars, where the day side gets enough heat to melt ice while the rest remains frozen. Climate models suggest that if the atmosphere and oceans are not too thick, such a pattern could be stable over long periods. The result would be a planet with extreme geography: open water in one place, ice fields beyond, and permanent night on the far side. Eyeball planets are still theoretical, but they help scientists imagine what habitability might look like under unfamiliar conditions. Some proposed worlds are stranger still, with interiors so rich in carbon that they may produce gemstones. Diamond planets are hypothetical or proposed worlds with unusually carbon-rich compositions, where high pressure could turn much of that carbon into diamond deep inside. They are not giant glittering jewels from surface to core, but under the right chemistry and pressure, diamond layers could be a major part of their structure. These planets may form around stars with carbon-rich material, or they may be the stripped remnants of larger bodies whose interiors are exposed. One famous candidate is 55 Cancri, though its true composition is still debated and may be less exotic than early headlines suggested. Another often mentioned case is PSRJ 1719-1438b, a dense object orbiting a pulsar that may be the carbon-rich remnant of a former star. Diamond planets remind us that planets are built from the chemistry of their birthplaces. Chemistry can also affect density in the opposite direction, creating worlds that are oddly swollen and light. Puffy planets are worlds with very low density for their size, meaning they are swollen far larger than expected compared with their mass. Many are gas-rich planets, orbiting close to their stars, where intense heating inflates their outer layers. Their gravity is relatively weak at the top of the atmosphere, so the gas expands and becomes extremely extended, making the planet look oversized. Some are so diffuse, they have been compared to cotton candy. WASP-107b is a well-known example, with a size close to Jupiter's but a much lower mass. These planets challenge simple models of how atmospheres behave, because heat from the star, internal energy, and atmospheric escape all matter at once. Puffy planets are valuable to astronomers because their large atmospheres are easier to study when starlight passes through them. If heating and escape continue long enough, a gas giant can be stripped down to something even more extreme. Chthonian planets are the possible leftover cores of gas giants that have lost most or all of their thick atmospheres. The idea is that a planet like a hot Jupiter orbits so close to its star that intense radiation and stellar wind gradually blow away the outer gas. What remains could be a dense, rocky, or metallic core exposed to space. These worlds are hard to confirm because they may resemble large, rocky exoplanets, but the concept helps explain how some close-in dense planets might have formed. The name comes from a word linked to the underworld, fitting for a scorched remnant left after a giant planet is stripped bare. In a sense, they are planetary fossils that preserve evidence of a more massive past. They show that planets can change type over time, not just form once and stay the same. That same idea of mixed identity appears in another proposed class, with deep oceans and hydrogen-rich skies. Hycean planets are a proposed class of exoplanets that may combine a hydrogen-rich atmosphere with a global ocean covering much of the surface. The name blends hydrogen and ocean. They are often thought of as larger and hotter than Earth, but still potentially capable of hosting life in some conditions, especially if the ocean remains liquid beneath the atmosphere. Because hydrogen is light and can create a strong greenhouse effect, a Hycean world might stay warm even farther from its star than an Earth-like planet would. Some could also be tidally locked, with habitable conditions in a band, or on the night side, rather than everywhere. K2-18b has often been discussed as a possible Hycean candidate, though its true nature is still under study. This category is new and debated, but it gives scientists another way to think about where life might exist. Some planetary objects go even farther from the ordinary, forming around black holes. Blanets are hypothetical planets that could form in the disks of gas and dust around black holes, especially supermassive black holes at the centers of galaxies. The name combines black hole and planet. In theory, if parts of those disks cool and clump in the right way, they might build planetary bodies, much as ordinary planets form around stars. These worlds have not been confirmed, so Blanets remain an idea rather than an established observed class. Even so, the concept matters, because it tests how flexible planet formation really is. If nature can make planets in such extreme environments, then planet building may be one of the universe's most adaptable processes. A planet would orbit a black hole not because the black hole is a star, but because gravity works the same basic way on any orbiting body. From planets around black holes, the next step is to worlds already known around another exotic object, pulsars. Pulsar planets orbit pulsars, which are rapidly spinning neutron stars left behind after massive stars explode. Pulsars beam out regular pulses of radiation, and tiny timing changes in those pulses can reveal orbiting planets with amazing precision. In fact, the first confirmed exoplanets ever discovered were pulsar planets, found in 1992 around PSRB 1257+12. Their existence shocked astronomers, because a supernova seems like the last place a planet should survive. Some pulsar planets may be survivors of the original system, while others may have formed later from debris after the explosion. Conditions near a pulsar are harsh, with intense radiation that would make the surface environment extremely hostile. Even so, these planets proved that worlds can exist in places once thought impossible. After seeing planets survive around stellar corpses, it is fitting to end with a type defined not by weird physics, but by the possibility of being even better for life than Earth. Superhabitable planets are a proposed idea for worlds that might offer even better conditions for life than Earth does. They are not a confirmed physical class like gas giants, but a habitability concept based on features that could make life easier to start and persist. A superhabitable planet might be slightly larger than Earth, giving it stronger gravity to hold an atmosphere, and a bit older, allowing more time for life to diversify. It could orbit a stable, long-lived star that is calmer than the young sun, and it might have broad, shallow seas, active geology, and a climate that stays mild for billions of years. In other words, Earth may be good for life without being the absolute best possible world. That idea changes the search for life by reminding us not to look only for Earth copies. The universe may be filled not just with many kinds of planets, but with worlds that outdo our own in habitability.